Hello everyone, this is episode 2 of Advent of Code 2021, and we'll be solving the tasks from day 2 through 5 in this one. If you don't know what Advent of Code is, I encourage you to watch the previous episode in which I explained the rules and I also showed the first task. Without further ado, let's get to it. On the second day, the task that we got was relatively simple. We got a list of commands which were forward, down, and up. And these were literally what you think they are. We are just moving something in two-dimensional space. So basically moving to the right, moving down, and moving up. And we were supposed to just start from like 0, 0 and travel through space using every one of these commands. And in the end, the result of the task of the first half would be the product of the target position, like the target X and Y values. I started by pasting in the example input and I made some case classes for the commands and the application state. I also added a calculation of the result because that was a simple task. Then I proceeded to implement the logic of a single command as a state transition between one value of the state data type to another value of that type. So in the forward command, we would increase the X value. In the up and down commands, we would change the Y value. At this point, I wanted to have some data to actually run this code through. So I started the parsing. And initially, I wanted to use normal regex, but I realized I could use the Scala213 feature of string interpolation in extractors. So I used that and parsed my text to my commands. Then I parsed my file, run a fold left starting from an empty state with 0, 0, and passed my state modification function. The result that I got from the example input was correct, so I used my real input to get the final result. The second part changed the behavior of all the commands. Now the down and up commands would change the aim, which is a new parameter which also starts at 0. So I added that to the state. In the forward command, instead of just moving the x-axis, we would do that, but also increase our depth, so our y-axis, by the aim multiplied by x being the parameter of the command. I copied my state transition function and made it do just that. I ran the code with the example input and got the right answer, so I changed it to use my real input and used this to submit my solution, and it was correct. Now in the refactoring afterwards, I made some renaming to change the state class to upstate, and then I wanted to use the state monad for my state transitions. This could have been overkill because we have really simple state transitions, but I wanted to do this anyway, and this might actually be something new to you. So you might have something new to learn. So given that I now had a monad to use, I could traverse my input with state. I have a video about this. I should link it somewhere here. And yeah, I did that and got the final result using run s. And here eventually I made a generic function that takes a state transition as a state monad and reused that between the two parts. And finally, I made some more renamings and structure changes to make the code look better. For day 3, I was actually up very late and I was still up at 6 a.m. so the task unlocked in front of me. And boy, this one was tough. I really didn't want to solve it at 6 a.m. but here we are. Long story short, we got a matrix, two-dimensional matrix of binary numbers, so zeros and ones. In the first part, we were supposed to find the most common character in every column. And then we would have to do the same, but in reverse. So find the least common character in every column. Then out of the most popular bits in every column, we would make one large number. So given like 5 columns, we would have 5 bits for a new number. We would combine that and turn that into a decimal number. And we would take these two values and multiply them in decimal. And that was the final result of the first part of the task. So I took the example input and put it into a string and tried to parse it to a matrix. So I split it by lines and then to the characters. Initially, I just went with chars. I didn't convert to booleans or any other type for bits. And I realized that to find the most common or the least common character in every column, I could transpose the two-dimensional array and find the most common elements in like the top level entries. So for every line, which is now basically what we originally had as a column, I would group it by identity and take the max value of that map by size, and then extract the key of that entry, which was the original character that we needed. I realized the output was the same as the example, so I took my real input and tried to use it. So I turned my result into a list of binary numbers and tried to parse it to a decimal integer. I took that result and submitted it as my solution, but it was wrong. Turns out that I had completely missed the fact that I needed to find the least common bits as well. I thought that was really smart because I wanted to flip the number using the binary inversion operator, but then it actually changed the sign of the number as well, which made sense because the integers in Scala are signed. If I had an unsigned type for numbers, this would probably work. But I didn't have that, so instead I wrote the code to find the least common number now and basically duplicated the whole thing. All this made sense because I was supposed to have two values that I would multiply by each other. And this got me to the second star. Now this one was even more complex. So here we were supposed to keep the numbers that matched the most common bit in the first position, then like take the result, like the numbers that we kept, and filter them again, but based on the second bit, then the third bit, and so on. So we would basically incrementally reduce the input to one number, and when we found one number, that would be the result. And we would do the same for the least common numbers, so we would filter the input by the first bit, find the ones that had the matching bit, the same one as the least common one in that column, then proceed to the second bit and so on until we found exactly one element. One thing I didn't notice at first, as you'll see, is that when there's a tie, when there's an equal amount of zeros and ones in a column, we were supposed to do something specific. In the most common case, we would just fall back to 1 in that case. Like this is what we would be filtering by. And in the least common one, we would filter by zeros. So if there's an equal number, we would keep the numbers that had a 1 or a 0, depending on which part we're solving. It took me a while, but eventually I figured out what I wanted to do. So I made a recursive function, which I would call once for every bit until I found the result. It ended up taking the index that we were currently at and the data after filtering from the previous round. Inside, I would filter the data that I currently had to only find the entries that matched the bit that we are currently looking at, the ith bit. If that found exactly one element, I would just return it, but if it found more, I would recurse with the index increased by 1. I called that with my data, but I got a really weird result. I ignored it for now. I copy-pasted the code to do the same for like the least common character, and I spent a lot of time not calling the right method. I was calling the same thing, like go for both kinds. Meanwhile, I was supposed to call go and go to. I thought I was actually done, and I used my real input, but I got the wrong answer again. I initially thought I was maybe overflowing the integer type, so I changed my numbers to longs and multiplied them that way, but that wasn't it. I was actually just calculating the results wrong. I realized I was getting a 22 when a 23 was expected. And it was only then that I realized I was supposed to resolve these tie breaks. But I wasn't even getting ties, like there was never an equal amount of elements in both brackets, like in the ones and in the zeros, because I was always using the most common statistics or the least common statistics for the original input, not the filtered input. It took me probably like 10 minutes to realize what was wrong. I first added this tie resolution logic, but I still didn't realize I was using the wrong stats, and the 22 is still a 22. Eventually, I realized I was not supposed to use the original stats, I was supposed to recalculate them at every round. So I copy-pasted the code that would calculate the most common bit in every column, and I inserted this into my recursive function, and it would now use the data from the previous round. I removed the whole part of the code that was responsible for the least common part and just put a copy of the most common stuff, but replacing everything with like all the max to min and so on. And I made the same stupid mistake again. I still forgot to call the right function. So instead of calling go to recursively, I was calling go. This would have actually been much easier to spot if I had annotated my functions as tail recursive, which I will do much later, but at this point I didn't. So after like 10 minutes of looking, I realized I was just missing a single character. So I added that and got a result. And at this point, I was almost out of battery and I was in my bed with my laptop. My example input was now correct, so I changed the data to my real data and I got the number, I submitted it, and it was finally correct. So I went to sleep. It was 6:30. I was really tired, exhausted, and I said I would never do this thing, like staying up this late, again. But I'm not really good at keeping promises to myself, so I did the same exact thing for the next 2 days. But first I had to clean up my solution because the current one was terrible. I really made a lot of small changes, incremental changes, that I don't really want to talk about. They are not that interesting, but I'll tell you about the major ones. So there was quite a lot of duplication of the code for finding the most common and the least common bits in the input, in both parts actually. So we had like the same code probably 4 times. And the only difference was actually that we would look for the most common or the least common stuff. So I defined a data type called mode, which would have these 2 modes, max and min, and changed the code to use that to decide on the exact logic being applied. So when this was max, we would find the most common characters, and we would also use 1 as the tiebreak. But if it was min, we would be finding the least common bit and also using 0 when there's a tie. Eventually this was good enough to just have one go method, which would be used for both pieces of the second part. Then I extracted the bit of code that was actually finding the most common or the least common bit in the input, and I used that in part 1 as well. So now we had all the code using the mode logic, using a single method that actually did all the work, all the grouping and counting and so on. I actually spent a moment adding comments to better understand what I'm actually doing here, and so that I could maybe bump into another idea for refactoring. And I think in general it was a good idea to add this kind of stuff. I also spent a little bit of time on the naming of the variables so that the tiebreak logic was explicitly saying what it actually does and so on. Another thing I wanted to do is reduce the potential for errors. So instead of using a data type that has quite a lot of values, which is char, I wanted to use booleans. As a step of preparation for that, I extracted a type alias called data, which was basically a list of char, and eventually I would change it to a list of boolean. And I did that. It was quite straightforward. Like I actually needed to add the parsing from a char to a boolean in the middle of the code, but I was able to basically expose booleans in all the top level methods instead of just chars or strings. Later on, I actually made quite a lot of this code polymorphic, so I wouldn't even deal with booleans, but it was just some generic types. But I'm not going to show that here. You can actually look at the repository if you want to see that. But I still made some changes, so I didn't really like that I was doing manual recursion. I added a tailrec annotation just to make sure that it's correct, but I wanted to refactor this code anyway. So I decided to use tailrec n. Long story short, it's a way to recurse in a monad. In here we have the ID monad, which is basically just the type that it's wrapping. So ID of A is A, so there's no monad at all for this. But it was enough to allow us to reuse the pattern. And basically, you provide the data that you start with, and then you provide the function that returns either a right with a final result, or a left with the next value to recurse with. So exactly what we had. Instead of just calling the function recursively, we would return its parameters actually, and that was pretty much the same thing. And the implementation of tailrec m would take care of the recursion for us. At some point during this process, I realized I had a bug. I had left and unchecked like a comparison of 2 types that were unrelated ever since we switched to the boolean type, and this was actually the reason why there was still a 22 in the logs, not a 23 as expected. Somewhere at this point, I realized I didn't need to deal with the indices so much, so I could actually extract the logic that did the index lookup, like finding the bit of the currently processed index. Like this didn't need to be in the code that did all the dirty work. This could have been passed from the outside. So I passed the function from list of boolean to boolean instead of the index, and it worked. I also wanted to try a different approach to the whole recursion problem, and I was wondering if I could actually traverse to state just like in the previous day's solutions. Even if I had something to traverse on, which I later used the indices of the first line for, I still needed a way to exit early when I found the single row that matched what I wanted to find. And I realized that I could compose the either and state monads together, and depending on how you combine them, like whether it's either t of state or state t of either, you will be able to make changes to your state and exit early, or you may be able to have a state transition that may completely fail. So I wanted the first thing, so I had to use either t with state as the underlying effect. underlying, as in like it would be wrapping the either. This approach wasn't actually much cleaner. I would argue actually that it was not cleaner at all. It was probably even worse than the previous one, but I wanted to keep it anyway. This required me to have like a fallback, like when we traverse but we still don't have a result, I would need to do something to get a value. So I would just throw an exception because this shouldn't happen in normal situations. One good thing that this whole exercise did for me was made me realize that I could use a state monad for just the state transition between the lists of data. So the shared code, the code that was used in both of these approaches, would be a state transition. It still was, but it would be very explicitly a state transition or a value of the state monad based on the state of the data. So the list of Boolean would be our state, and we would return unit because we only want to modify the data. We would then retrieve that data on a higher level to get to look at the remaining values. And if there was something in there, like one result, we would just complete. If there were more, we would recurse again. So I finished up that alternative solution, and that was the end of the day. For day 4, I was actually still awake at 6 a.m., so I waited for the task to start, and I wanted to solve it immediately. In this task, we actually had something like a bingo game, and we got basically a list of the numbers that were called and the list of cards. The cards would be a two-dimensional array, like every card would be a two-dimensional array of numbers in columns and rows, and the calls would be comma-separated numbers that were called. And in our first task, in our first part of the day, we were supposed to find the card that was finished first. And the condition for finishing a card would be to have a full line, like either a column or row of numbers that were already called. And the final result that we were supposed to submit would be the sum of all the numbers that were not called on that card multiplied by the last number called. I took the example input and started parsing it. So basically I took the first line, split it by commas, and I made a list of numbers based on that. So these were our calls. Then I took the rest of the input and split it by 2 new line characters, which turned out to be sufficient to get the boards separated. For every board, I would split it by the new line character, and inside I would split by white space. So I got, in general, I got 3 levels of arrays. The outer array was boards, the next array was the line of every board, and the next one, the most deeply nested one, was elements in that line. I made a data type for boards, which was a 2-dimensional array, so I finally got a list of board, and that was my input. I made sure I had exactly 3, as in the example input, and I defined the data type for the state that we were going to have across the whole application. Initially, I made it hold the remaining calls and the past calls. So the 2 lists together would be the whole input that we originally had, and we would just transport items from one list to the other. But I actually removed the remaining calls because they were useless, so we only needed the past calls. And that was a list, so on top of the list, I would put the latest call because I knew I would need that exact value later. And keeping it on top of a list meant I had immediate access, constant time access to that element every time, which is just to say it was optimal, but with the size of data that I had, it wouldn't actually make such a difference. At this point, I decided to write the logic that would check whether the board is complete. For that, I needed the value of the state, or at least the past calls, because these would be the values that were needed for this board to be complete. Like we would actually check every element of the board, like of the board rows, and check whether all of their contents are in the history. So I would do this for rows. So this would actually allow me to see if the board is complete thanks to having a full row. But then I would need to do the same for columns. So I did the transposition trick again, and that was good enough to do the same thing for columns. So we would just transpose, and now every entry in the top level array would be a whole column. So we could just check whether all these items are included in the past calls of the state. I didn't do this, but we could have further optimized the state that we had and keep just the last call, and the rest could be a set, because that way we would have faster lookup in the set, and also we wouldn't keep duplicates, which we didn't actually need. At this point, I had almost all I needed to solve the whole task, so I would traverse all the calls using the now familiar pattern, traverse to state, and we would deal with the state monad of the state data type, and we would just change that. So the state transition would always be the same. We would prepend the latest call to the previous state, and that was it. But also, in order to find the solution, we would check whether any of the boards are actually complete with the new state. I actually had a bug here for a while because I was setting the new state to the old state, so I was effectively not changing the state ever. I was trying to debug this problem for a while, so I was printing like the current state of the board, or maybe printing just random numbers to say whether I was actually calling this function. But eventually I printed the history in that method that was checking the completeness of a board, and I realized it was always empty. So that made me realize I was never actually modifying the state. So it was the empty list that I started with. Finally, I realized my mistake and I fixed it, and that code was actually now changing the state correctly. But I still didn't have an exit condition, so I'd just traverse all the calls until the very end. So I needed a way to return the result and also not traverse all the calls. So I found the result and I printed it, and then I just threw an exception. And in order to not see the exception stack trace in the running of the code, I actually called it using the try monad, and I completely ignored it. Do not do this at home. So I got the board that was in there in the example, that was the last board, and that was correct. Now I needed to calculate its score in order to have the number that I was supposed to submit. Again, the score would be the sum of all uncalled numbers on that board multiplied by the last called number in the state. So in the implementation of that function, I would flatten all the fields in the board so that I would have basically all the numbers that were on it. And I only kept the ones that were not in the state in the past calls. And to get the proper result, I multiplied that by the most recent call. So basically whatever was on the head of that list. I checked the score for the example input, it was correct, so I took my real input and pasted it into my code. Then I used that to get the score for my input, and I submitted the result. It was correct. Now for the second part of the task, there was just one small change. We were supposed to find not the first board that was complete, but the last one. The way that I had written this code actually made this much easier than it seems. I knew that all I had to do now was wait for the moment where all the boards are complete, and when they are, find the one that was not complete on the previous state. And because I was using immutable state and I was using the state monad, I still had access to that value, so I could still use the past state to verify this, to find the board that was not complete in the previous step. So I found the board, I printed its score, and I threw an exception and I called it in the top level again. So we did the same thing as in the first part. So I got the right board, I printed its score, but it was still incorrect. And it took me more time than I'm willing to admit, but it was not correct because I was using my real input instead of the example input. The example input would have been actually fine. So I switched back to the example, I switched back to the real input, I took the result and I submitted it, and it was right. So I really felt like this day's solution wasn't as dirty as the previous one, even though I did have that hack with the exception that I was throwing and catching and just ignoring. It was still not as bad, it was still a decent solution. Most of the refactoring that I did on this was actually minor changes, some renames, and some like reusing some of the code, like finding the rows and the columns that were full. I basically extracted a function that would you would just have to do rows and rows transpose, and you would pass the same function to both of these arrays. I also made the board and the state generic in the elements, so we didn't really need to know that they were numbers, we just needed to know that they have the numeric type class for them. Not only that, we actually didn't need the whole power of numeric for the isComplete function, we only needed the equality of that. But that was included in numeric, so I used that, but we could have just as well used the eq type class from cats, or something similar. Actually, the whole code that did the logic for this day was also polymorphic. It also didn't realize that that the element of the board was actually a number or an integer. It could have been anything really. So we only knew that it was integers in the parsing stage and also in the code that wired the parsed code, the parsed values into the logic of the solution. While working on this, I became so annoyed with the tooling that I had currently with Scala CLI. For some reason, it didn't collaborate well with the editor, so I just switched back to SBT. Now, all I had to do to be happy with this solution was get rid of the exception that I was throwing and use something better. I actually wanted to do the same thing as in the previous day, so use something like a combination of the state and either monads, but I didn't really like the way that I was composing them, like manual monad transformer composition. I wanted to use something more principled and something easier to maintain. So I pulled in catsMTL and I used the stateful and raised type classes. Using these type classes, I was able to keep the functionality of the underlying effect, the composition of the two monads, without the complexity of using monad transformers. Well, at least without the boilerplate, and the complexity would still be there, but it would be pushed further up. So I would only have to specify the exact effect on the top level. So now, instead of printing the result and throwing an exception, I was using raise to specify the result of my call and also interrupt the whole execution so that we would be basically done at this point. However, the code still only supported the second part of the task, but not both of them. And I used the same trick as in the previous day. I used an enum for two ways of solving the problem. Here I called this end condition, and based on the value of the condition, we would find either the first or the last board that was completed. And also we would either keep running or wait for all the boards to be done. When it came to running the state monad, I realized I could use something like run MTS, or instead of just run and providing a value, if I had a monoid for my app state. Because app state was wrapping a list of a generic E, I was able to have a monoid for any E, because we can get a monoid for anything that's basically a wrapper over a list. And it doesn't even matter what the type of the elements of the list is. This is because list is called sometimes a free monoid, and also because app state is isomorphic to a list, which means that we can convert to and from it with no loss of information. I actually use that fact to map on the monoid instance of list by wrapping and unwrapping it into app state, which was basically isomorphic map, you could call it. And this gave me a monoid of app state, so I was happy and I could proceed. In the end, I used run empty because I needed both the final state and the output of the whole program. The output being the board whose score we were going to calculate. Technically, the output was an either, and it could be either a left with the board or a right with unit, but in practice, the right should never be there. This would just mean that we either messed up the implementation or the input data is incorrect. And in Advent code, you always get correct input. So because this was an exceptional case, I just threw an exception because I didn't expect this to happen in normal conditions. And here I actually made a bug. I was multiplying the score of the board by the most recent call again, even though I was already multiplying the sum of the uncalled cells in the board by the most recent call, so I was basically multiplying it twice. But I didn't realize that until much later. I did notice my data was wrong, the outputs were wrong, so I thought it would be nice to have some sort of assertion framework so that I could write down the results that I'm supposed to get, and when any of them changes, I will be aware of that as soon as possible. So I added an assert equals method to my lib object, which would take two values which were supposed to be equal and a description of what these values are. For example, it would be part 1 example, part 2 example, or just part 1, part 2. And if the values were not exactly the same, we would print a value to standard error output, but we would still continue running the rest of the code. So the whole function would return unit, it would just make the check and either print a successful message or a failure message to the error channel. And it was only at this point that I realized what I was doing wrong, that I was multiplying the score of the board by the most recent call twice. So I removed that and I was now getting the correct results. I made a change to the assertion method that I defined so that in the successful case, like if the result is what it should be, I will have some sort of green pre-printed message. And at this point, I decided to call it a day. The next day, it was December the 5th, and I did it again. So I stayed up until 6 a.m. and I waited for the task to begin. This one had a relatively easy to parse description. I actually kind of understood what I was supposed to do much sooner than usual. And basically it boils down to the fact that the text that we got was a description of lines, of actually like segments between 2 points on a two-dimensional space. So in each line we had a description of a segment between 2 points, inclusive. So these would be either perpendicular to the x-axis or the y-axis, so either equally horizontal or equally vertical. Just kidding, we would also have diagonals, but we were supposed to ignore them for the first part of the task. But I knew that eventually, because they said that, like ignore them for now, this would be useful or actually necessary to handle in the second part. Every segment would include like only full numbers between the start and the end point. So for a line like 0, 0 to 0, 2, we would have exactly 3 points, 0, 0, 0, 1, 0, 2. And the goal was to find the amount of points that appeared on more than one segment. For this task, I had already prepared SBT and metals worksheets, so I was going to use that to solve the whole problem. Thanks to this, we would see not only the live refreshing value of the whole task, like the final output, but also every val that I defined in between. So I started by parsing the input, so every line would be just a line case class, and every point would be a point case class. So a line, or basically what corresponds to the segments, would be a case class with 2 fields, 2 points. Again, I used the string interpolation kind of parsing, the extractor, using case as quotes, which is a new feature in Scala 2.13. I think it's a great feature and I will be using it as long as it works. For now it's sufficient, but when we move to more advanced parsing problems, we'll need to use something else. So I needed a way to find out if a line is completely horizontal or completely vertical. I added methods called sameX, samey to say exactly that. And I filtered the input to keep values that matched one of these two conditions. In order to find all the points that overlap, I knew I needed to have a way to find all the points on a line. So I used the checks that I defined before to decide how to find these points, and I would not handle the diagonal case for now. Initially, I just made ranges from the starting point to the end point using the x or y value. So in the case that the x doesn't change, we would just change the y's. I would just copy the original point and change the y value, and vice versa if the y didn't change. But later I realized this was wrong, because if from y was smaller than 2y, we would just get an empty range. I would need to actually make sure that the ranges are starting from the smaller number and ending with the larger number. But let's ignore that for now. I went to the part where I would find the points that appear on more than one line. And in order to do so, I would basically assign a number to each line, like an index of it. And I would flat map my list of lines to basically a list of all the points, but every point would keep information about which line it's coming from. I later realized that I didn't really need the index, because if the point appears twice in this final flattened list, it's already overlapping with something. Like, it's already a result of some segments overlapping. But it didn't really hurt. So at this point, I needed to find the frequency of every point in that final list. In order to do so, I would group by that point, and then map the values of the resulting map to the size of the set of points that match this condition. So basically flatten a list of equal points to a single number. And given that number, I would just count the amount of these values that were higher than 1. At this point, I thought I had all I needed, but the value that I was getting was too low when I was running the example input. And this was because of the problem with ranges, so I fixed that by doing a really quick hack, just checking which number is larger, and if the target number was larger, I would start with the source number and otherwise. So this ensured that the ranges were not empty and a line actually had some points in it. And that was enough to fix the problem for both the example input and actually also my real input. So I submitted the result and I got to the second part. And in this one, as I mentioned before, we were going to actually use the diagonal lines. In fact, that was really the only change. So the diagonal lines basically worked like in chess, so you could only go like one step up and one step right and so on. You would always change by one both axes when you were going to another point. And I made quite a few attempts, I think like 3 different approaches to doing this, but eventually I figured out that I would need to do something like the following. I used the horizontal direction to just iterate from the smaller number to the larger number. So basically what we did for the previous task in the case where the line was completely horizontal. But then instead of going with the same vertical value every time, I would do something else. I would have to determine which point I started from, so which point the smaller x was from. And if it was the starting point, the from value, I would start from the y value of that exact point. Otherwise, if the smaller x belonged to the to value, I would use that value's y to begin my y adventure. In both cases, I would have to do the same trick to determine which point to start from when I was making my range. But in the end, the y that I was going to use was the smallest y that we had in the segment, plus the index of the current point. Or it would be the larger y minus the index. This is actually wrong on the code that you're seeing now. You'll see it corrected later. So for the first point, we would add 0 because it was the start of the segment. And according to the same rule, the last point would be the end of the segment. This is severely overcomplicated, and I realized that when I was fixing this code a couple hours later, but I think all of us would write this kind of code at 6 a.m. So believe it or not, but this actually worked and got me the right result in the example case. And then I changed it to use the real input, and I got the correct result. To start the refactoring process of this day's tasks, I added some assertions using the library that we defined the previous day. This would allow me to quickly verify whether the solution still works the way it's supposed to. When I initially solved the problem, the code that was doing all the processing was just a val that was processing the data val, which came just from parsing the input. And the input was chosen just by commenting or uncommenting a line. But at this point, I wanted to pass the value as a parameter to a function. So I made my result thing a function instead of just a val, and it took the data as an argument. I also thought that I could use this to pass the argument filtered or not in the first part. Like in the first part of the task, we would just keep the lines that were straight, like fully horizontal or vertical, and we could do the filtering at the call site of the result function. And we could, but I didn't want to repeat that code twice because we would do the same thing for the example input and the real input. So I made it a function that would take a list of lines and return a list of lines. I made sure to read and parse the inputs of both the example and the real stuff, and I passed the example data to the no-diagonals function, the same as I would pass the real data to the exact same function. Around this point I realized I didn't need a worksheet anymore, so I just made the whole thing a full-blown Scala file. I added the main class and I was using that to run the program in Bloop. Then I realized that most of these functions that I had could be written in point-free style, so we would just basically make them use an anonymous parameter and just do a chain of dots. This had the extra benefit that it was easier to compose these functions together. In Scala 3, actually, this wouldn't have made a difference in that matter, but here it actually did. So I composed my functions in a way that allowed me to get a function called part1 and part2. And they actually took the raw input, the text input. They only needed the strings in order to produce a result. We could probably even take just the name of the file, but then we would have to read each file twice. Now it was time to actually simplify the code that generated all the points on the lines. I wanted to start with the toughest part, so I did the diagonals first, and I thought I had a really nice idea. In order to find the smaller number out of from x and to x, I would put these two in a list and sort them by x. This significantly simplified the way that I was doing like min and max. I wouldn't have to repeat this twice. So start.x to end.x would be my x's. I remembered that ranges can actually go backwards if you specify the step of them to be a negative number. And in the end, I was able to just calculate the sign or the number, like the 1 or -1, based on whether the start point is first or the end point is first in terms of the y-axis. And at this point, making the range was really easy because I just did start.y to end.y, and then I used the sign to determine the direction that I was going to. Then it was just a matter of zipping the two lists to produce a point for every element that appeared in both lists. And you can do that using the zip method and then mapping on it, but that's not very convenient in Scala 2 because you need to destructure the tuple and so on. Instead, I did parmap n from cats. This works perfectly fine and didn't force me to do that. For the easier lines, I also used the approach of sorting in a list. And then here it was just enough to use that to determine the range of y's or x's because the other number was constant. And I made a helper to do this kind of list sorting and creating range thing because I didn't really like destructuring the list twice. And that was actually it. I decided I was done with this day's tasks. Thank you for watching. I hope you enjoyed these solutions. If you have some more thoughts or some more ideas for solving these, I will happily read them, so let me know in the comments. Let me know if you liked this and leave a like, subscribe to the channel, let your friends know, and I'll see you in the next episode.